Hello everyone, welcome back to another video. In previous video, we learned about Boolean theorems, and in this video, we will learn about duality theorem. And we will understand duality theorem completely by solving different examples, and you will all your doubts will be clarified after solving these examples. So, coming into the topic, what is duality theorem? And duality theorem is it states that in a Boolean expression, if and is replaced by or is replaced by and not is replaced by not, then the new expression will also be true. So, let us take an example. I am taking a plus a bar b. Then what I can write that way, if I am replacing or with NAND, then that will be A into, and this AND with or, A bar plus B. Then we can write that one as A into A bar plus AB. A into A bar is 0, so we will get A into B. Similarly, if we solve this one directly by using redundancy theorem, then you will be A plus not redundancy theorem. We have a Boolean formula for this A plus A bar will be A plus B. And if you apply duality this one, or is replaced by AND, then this one, and this one is equal to this one. This is what duality theorem suggests. So, what we have learned about duality theorem is if we are replacing and with or with NAND by solving the expression that we are getting after replacing those gates with respect to dual gates, then that expression will also be true. So what we can draw from this is, if I am replacing and, what we can suggest is and is the dual of or, and or is dual of and. Similarly, not is dual of not itself. So based upon this, we can write for universal gates and as well as arithmetic gates as well. So if I am taking and or, so for NAND, what will it be? And not. So I am writing and NAND. It will be dual of not plus or, that is NOR. And similarly, NOR will be dual of NAND. XOR is dual of XNOR. So I think you understood what is duality theorem. We will clearly understand duality theorem by solving some problems as well. So here is a problem that we need to solve. Here given function f of ab is a plus b bar in dot a bar plus b bar, and we need to find the dual function and the complement of f of ab bar. So first we will find the dual function ab. That will be, we will replace this or with an and b bar, and this and with or, a bar plus b bar. Sorry, it is not a bar plus b bar, it's a bar into b bar. If you are taking b bar as common here, then you will get a plus a bar. That will be a plus a bar will be 1, and 1 into b bar will be b bar. Similarly, we will find the complement of a bar, f of ab whole bar, and we need to find complement. So a plus b bar into a bar plus b bar whole bar. So what we will get here, if you are applying De Morgan's theorem, change the line for b bar whole bar. Yes, and this will be turned into or get, and a bar plus b bar whole bar. We have break the line here, and similarly we will solve for this one as well. Then you will get a bar into b plus ab, and here we will getting b common, a plus a bar, that is equal to 1 and equal to. Based upon this problem, what we can understand is that the dual function of a given function will always not be equal to complement. And similarly, we will solve the problem. We are finding the dual function of f of a comma b comma c. So first, fd of a comma b comma c will be, will replace this and with or, a plus b and or with and that will be b plus c dot c plus a. I think you understood here up to this one. So we will keep c plus a as it is, and we will solve this one. Then that will be ab plus ac plus b into b plus bc, and that will be into c plus a. And then if we take b as common here, b into b will be b itself, b into b will be b. So what we will take here, we will take b as common, and what we will get, a plus c, b of a plus c plus ab into c plus a. Sorry, here we will get 1, so it will be 1 plus anything will be 1, so b into 1 and b plus, sorry, here it is ac, b plus ac into c plus a. And similarly, if you solve this one, you will get BC plus BA plus AC into C will get AC, and AC into AC will get AC itself. So we will get BC plus BA plus CA, and this one is equal to f of a comma b comma c, and here the dual function is same as the given function. So what we can draw from this is that if a dual function is equal to the original function, then that function is known as self dual function. So I think you understood what is a self dual function from here. If the dual function that you are obtaining is equal to the for given function, here you can write BC, you can write BC is for here, and BAB you can write as BA, and CA as it is. So this function is equal to function of f. So this function we will call as a self dual function. We can write this as fd of abc is self dual of f of abc. So similarly we will try to solve this problem as well. We need to find fd of a comma b comma c, fd of a comma b comma c, and that will be equal to a plus b into b plus c, and if you take b as common, that will be a plus c, and if you apply duality here, b into ac, and that will be, if you apply duality again, then that will be a plus b into a sorry b plus c. So let us, from this what we can write, fd of a comma b comma c is not equal to f of a comma b comma c. Since f of a comma b comma c is a into b plus b into c, and here what we are getting is a plus b into b plus c. These are two different functions. So this may, this time at this for this solution, fd of a comma b comma c is not equal to f of a comma b comma c. So by solving all these problems, we can understand that in some cases f of a comma b comma c is equal to fd of a comma b comma c. Sometimes f of a comma b comma c is not equal to fd of a comma b comma c, but sometimes fd of a comma b comma c will be equal to the complement of a comma b comma c. So this is the duality theorem in whole. If you understand this topic perfectly, then you will understand, you will be easily able to solve the duality theorem problems. So one of the most important topic is, if they will give an equation and they will ask to find the number of possible logical functions and number of possible self dual functions in a given function. So for example, to I will give you the formulas to solve those problems. If you are given a two variable function, suppose n is equal to 2, if n is equal to 2, then the total number of possible combinations are capital N will be equal to 2 power 2 power n, that will be equal to 2 power 2 power 2, that is 2 power 4, that is equal to 16. These are the total possible combinations. Then what are the possible combinations, what are the possible self dual functions in a given function? In order to find for n is equal to 2, we will find number of self dual function. Self dual function will be represented with m, and that will be equal to 2 power 2 power n minus 1. So we will have 2 power 2 power 2 minus 1, that is equal to 2 power 2 minus 2 power 1, that is equal to 4. If you are having total n bit function, if you are having two variables, then you will have 4 self dual functions in that, and the total combinations that are possible are 16 combinations. So this is, in sometimes they may ask what are the if I am having a two variable function, and what are the possible number of self dual functions in that given function, then you need to apply this formula and you will get the answer. And these are two important formulas that you need to remember. And this one is 2 into 2 power 1. This is for total number of logic functions. You can you can get 16 different logical functions by applying duality theorem. If in those functions there will be four self-dual functions. This is how you will read the duality theorem. And if you get this one, you will easily able to crack all duality theorems, whether it may be gate or whether it may be any ESC or any PSUs as well. So in next class we will start logic gates. Thank you for watching. Stay tuned for next videos and subscribe our channel for more videos.